to be expected after the drop deadline. So in terms of announcements, this week I'm going to work a little bit on organizing projects. And what I'm thinking for the information is to find a way for you to submit your general availability when you can work on the projects during the work week. And I'll also give some ideas for what you could be working on. You don't need to commit exactly to those. But then also in that, let's say, form, you can mark what kind of topics you're interested in and whether you're an undergrad or a grad student. And then everyone can filter based on, let's say, availability, interest, and program. And in this way, you can more easily find what who would be a good teammate for you. So hopefully, I'm going to organize that by the end of the week. There is no really rush with projects yet. We have the project proposals a few weeks from now. I think what I expect is that you do find a teammate and start kind of thinking about what the project would be before the project proposal activity that's going to happen here. So do plan maybe like a week or two ahead of the project proposal, but still there's still a few weeks until then. So there is no rush, but we should kind of start thinking about that as well. Are there any questions from you? Yes.
I guess if we have like someone already in mind, we don't need to fill out the form, or do you want us to list it?
I guess, I haven't been thinking about that, but yeah, if you already have someone in mind, then submitting a form would be irrelevant because you would not be available anyway. Yeah, then you don't need to submit the form, yeah. Okay, and if you have any other suggestions about information, whatever, send the suggestions. Okay, so if there aren't any other questions, then let's continue where we stopped last time, which was generating descriptions for our SAE latents, right? And we have seen how that process works, but we stopped with how to actually evaluate whether generated descriptions are good or not. Okay. So let's do a little recap, and then we are going to come to the evaluation portion of that. So generating. I feel like these markers work better on my whiteboard than my ours. I'm having a little bit here. So just to repeat how this worked, we have a collection of tokenized sequences, right? So let's say we have call them P1 indicating first sequence, first token, second token in the first sequence, third token in the first sequence, and so on. Then we had first token in the second sequence, second token in the second sequence, third token in the second sequence, and so on. So let's use the notation T-I-J to denote J token in I sequence. So what we did then, what happened next is we passed each one of these tokens individually to our LLM and SAE. So every token goes through the SAE, and we get the sparse feature vector for that token, right? So we got the vector Z, and in this vector Z, we have value ZK for the token IJ, so J token with the I sequence, and we had a number of values in the sequence. We had as many of them as there are SAE features, right? Okay, so we got this sparse feature vector, and what we did then is we wanted to describe a single feature, right? So for every feature, so 1 to number of features. So for every latent, we wanted to get the feature description. So what we did for every latent was collect the set of activations. So we basically had collected the first value in every single one of these sparse feature vectors we have produced. And we have produced how many of them? Well, as many as sequences as we have, times number of tokens we have in every single sequence. So, for every token, we have from 1 to number of sequences times number of tokens. We collect, so we repeat this for every feature. We get the value zk, right? Because we're investigating k feature in that token. So we have a data set of these values, right? And then we have given those values to basically we have given token together with the value zk of that token to an LLM. And we haven't given just one, but a bunch of these, right? As many as we have. And based on all of these, LLM gave us a description of these features. So let me just make this a little bit more precise. So for every feature, for every latent in our sparse feature vector, we want to, and we have as many sparse feature vectors as we have tokens. Remember, sparse feature vectors change. The encoder and decoder matrices stay fixed across inputs. So for every latent, we want to provide a description for that latent. So what we do is we take all these tokens we have, and we have as many as them as we have sequences and tokens in those sequences. And to make this a little bit more clear that we are working with a data set here, I'm going to write here token from 1 to number of sequences times number of tokens, right? So I will have for a specific feature latent k, I will have this many activations for that latent. And then I pass all of those, so not just one, but all of those to LLM, and it provides me a pattern in those instances. So I will do this for every feature. And maybe here, I'll say description for k feature, or latent. Maybe it's I'm being a little bit imprecise, but maybe it's better to refer to the dimension of the sparse feature vector as latents, because we don't know a priori what these dimensions activate for, so they're kind of, their meaning is hidden, therefore latent is a good way to describe them. And then once we get the description of the latent, we can call it the feature. That would be the most precise way of talking about these things, but I'm being a little bit imprecise. Okay, so this is how we obtain a feature description. And now where we stopped and what we haven't, we started to talk a little bit about how to evaluate whether each one of these descriptions is a good description at the end of the last lecture, but it was a little bit rushed, so I will go over it slowly today. Are there any questions about the methodology itself, though? No. Okay, so now the question becomes how to evaluate this. Oh, this one keeps coming back. Okay. Let's see. So let's talk about evaluation. The first evaluation idea will be that if this description is a good description of when a particular dimension in the sparse feature vector will be active, meaning no zero, I should say higher than 0, then giving that description should be helpful for simulating what the activation will be, right? So if I say this description is expressions of emotions, like last time we have seen a feature that activates for like yay and things like that. If I give a bunch of tokens, a bunch of text to a LLM or a person, and I say, well, predict some value in some range from, let's say, 0 to 10 for every single token based on how active that token is for that particular description of expressing emotion. So, if I give you this task and you see tokens like you or yay or hurrah, you would probably give high activation values, some high scores for those tokens, and if you had neutral tokens that don't express any emotion, you would give something closer to 0, right? And if we do that exercise, we can then compare to what the actual activations were, right? And if there is a good correlation, then we can say, well, this description we have assigned to this latent actually describes well when this latent is active, which is exactly what we want, right? So let's make that more concrete with a more formal way of writing it. Let me just see how I wrote it for myself. Okay. So again, we are going to have a held out set of sequences that are tokens, right? So again, we start with, and when I say held out, that means sequences that I haven't used to provide those descriptions, right? So they have been unseen for providing descriptions. So we are going to see how well that description generalizes to unseen ones. So again, we have tokenized sequences. These are new tokenized sequences. So new tokenized sequences or held out. And so for each one of the sequences, again, we can compute what the actual activations are. So for every token, we can get actual sparse feature vector Z. And we are going to use that later. But what we are going to do is we are going to, for every feature, we are going to give it description together with a token. And we are going to request from some LLM, doesn't need to be the same LLM that gave us a description, to predict what the activation would be here. So now this LLM predicts value zk for this token ij. Okay, and let's call it here, let's give it tilde to kind of denote that it's different from the actual activation. So now I have the real activation of the Kate latent for that token, and I have a guess activation for the Kate latent for that token. What is a natural thing to do?
Compare that solution that we
Yeah, exactly. So we want these to be similar, right? We will give this LLM some range, but it can kind of have its own subjective notion of what is high and what is low still. So what you will see here typically is that people measure correlation between vectors of the simulated and real activations. So you can collect these activations and you can store them in a vector. Let's call it Z tilde. So this is vector of all. So we are iterating over ij. Let's call it Z tilde k. So for a given feature k latent, we can collect all of these simulated ones. activations. And we can use something like Peirce's correlation to measure correlation, and then if the correlation is high, close to 1, then we say this is a good feature of your description, otherwise it's not.
Should there be a tilde over that second ZK?
No, actually there shouldn't be anything back here. So we have simulated activations for the latent K, and we have the actual SAE activations for the latent K, and we want to compare this. Thanks for noticing that. So that's one way. The other way is very similar. Here, instead of measuring correlation and simulating what the activation value would be, you can actually try to predict whether for a given token and with a given description that feature is active or not. So another way, and you will see in the picture, let's write this to be way 1. Option 2, one that I'm seeing more often these days, is to actually have LLM decide whether the feature will be active or not. So, second option is to, again, for every K, you will have a description and some token. And you are going to use an LLM to make a decision between active or not active. And you can report accuracy for that particular feature. So accuracy for feature K is going to be basically average over number of these tokens we have. And we are going to pick 1 if we get prediction active, and ZK for that token, IJ, and here we're going over IJ, is larger than 0, and 0 otherwise. So let me just go over this. For every token, and we have tokens that I'm iterating over using I and J, so we go over number of sequences, which is I4, and J is for number of tokens in every sequence. So for every, maybe if it's easier, we can write here DIJ. So I'm iterating over all tokens. If my LLM here says, well, this, based on this description, this feature is active for this token, and if the latent ZK for that token is really active, meaning higher than 0, then I'm recording 1. Otherwise, I'm recording 0, and I'm averaging all of those, right? Yeah.
Where are we getting the description for our evaluation set?
Here, right? So
we're pushing them through that and then attaching the description to the token.
let me go over this one more time because this is important. So everything I said up to this point where I changed to this darker blue color was about a method that produces the descriptions, right? So everything here is how we get the description for a specific latent K, right? And now we have these descriptions, but we don't know whether these descriptions are any good or not, right? We need an evaluation that tells us we have assigned actually good descriptions to these latents. So we switch to the evaluation of the descriptions. Now that we have descriptions, we are checking whether they are good or not. And with this first method, we are checking whether the descriptions are, we can use them to predict what the activation of that latent would be for a specific token. And if they are a good indicator of how active the latent would be for a given token, we say the description was good. Right? And here is just slightly different way to operationalize the same idea. Instead of trying to predict the actual value, we are simplifying it into is it active or not, right? So here we will have only active or not, and we are reporting how many times we did our description help us predict whether the latent is active for a token or not. And if it's a good description of when the latent is active, here we should have very high accuracies, right? Yeah.
So in that case, would we also record it down if the latent was inactive and LLM predicted it?
Yeah, that's right. Thank you. So again, one active, and this is truly active or not active, and K for that token is smaller or equal to 0, and 0 across. Thanks. That's a very good point. Okay, let's make sure that this is clear. Is it clear that we have talked about how to produce descriptions, and then we switch to talking about evaluation of those descriptions? Okay, yeah. And then here we have two methods of how to go about evaluating those descriptions, right? Yeah.
Is one method preferred over the other, or?
What I'm seeing more and more, so this method is reported in a paper that I'm going to link in my notes. And they do have some theoretical justification of why this might be a better way of measuring, whether the descriptions are good or not. I find this one to be simpler and easier to interpret. So here, if you have a certain accuracy, you can say, oh, in this many cases, I have managed to predict whether the latent is active or not. It's really straightforward. Here, if you get a correlation of 0.9 or 0.98, it's hard to precisely describe the difference, right? Here, you can exactly describe the difference between accuracy of 90 and 95. You can say, with this methods of describing features, I managed to, this difference of 5% of cases was successfully, described with this method rather than some other method. So it's just more straightforward. I think that's why this one is also more frequent than in recent literature.
Couldn't the accuracy be affected by which LLM you're using to get those active or inactive predictions?
Totally, yeah. So here, if you are evaluating two methods for providing descriptions, so let's say we have this method for providing descriptions, but we are changing an LLM that's going to give me a description. Let's say once I use Claude Opus, the other time I use GPT 5.2. And I want to see whether, which LLM gives me better descriptions. So I want to use this methodology to do that. And then here it's crucial that you fix an LLM to say which one of those two LLMs was better for providing descriptions. Because if you change both LLMs here, then you have a confounder of what you don't know where the difference stems from anymore.
So you want these two LLMs to be the same when you're doing your evaluation?
No, that was not my point. Let me go over it differently. So we have two LLMs here. We have an LLM that is giving me a description, and I have LLM that serves for evaluation.
Okay.
For when you are deciding on which LLM to use here, you have many options today. So let's say you are deciding between a really powerful LLM like Claude Opus 4.5, which is really powerful but really expensive. And you're wondering, well, can I get the same descriptions if I use Claude Haiku? 4.5 still a good number for Haiku. So you are just wondering, can I get these equally good descriptions for way less money, right? Totally reasonable question you might have at the moment in time. So you need an evaluation metric, and right now you have learned that there is a way to evaluate. So what I wanted to say that here, you need to use not necessarily any of these. You can use GPT 5.2, for example. But if you want to compare these two, it has to be under the same LLM here. So you can't evaluate Opus with GPT 5.2 and Haiku with, I don't know, Llama 3 or something. That then will introduce a confounder.
Could they be the same though, or you know, is it not necessary?
They could, and probably in practice they often are, but the LLMs have been reported to prefer their own generations and have all sorts of weird biases. So I can't really specify right now on the fly what kind of bias that might be introducing, but whenever you want to use a same LLM as a part of your method, and for evaluating your method, that can cause issues. So it's always good to have a mix. Even when you want to have the same, maybe having another one, just to see whether the difference would be massive, and then that maybe gives you some ideas of, okay, maybe things are not great when I have the same LLM.
Question,
Yeah.
did the papers give any examples of where method 2 and method 1 diverge? Given something different, or some
Maybe.
correlation?
Maybe that's a good question. I wouldn't know, but that doesn't mean that no one had reported this. So again, in my notes, I will report the work that I had done a big kind of analysis of this method for generating descriptions, and maybe they did have some, insights on the divergence, but from the top of my head, I don't remember. So. Okay, so now, this is an actively evolving area of research, so there are even more methods, and we are going to go over 2 more. So, is this super clear? Because as I continue, the confusion will just propagate. Okay, generally fine. Righty, then let's go further. So we're going to now see 2 more ways how to go about this, and these 2 approaches come from a paper that was published at ACL 2025, so this is quite recent, and in general it's still evolving. So this is by no means something that the community agrees about how exactly we should do. So you might have ideas about how else to go about measuring descriptions, and they might be completely valid ideas. Okay, so, wait. So with this method, we are going to approach this from a data generation view. So you are going to have a description, and you are going to description for some latent K. And again, you are going to use an LLM, but here the LLM will be used to generate a data set of instances that activate this feature. So we will have a data set of activating examples. Okay, so previously we have started with a tokenized list of sequences, and some of them were active or not. Here we will give a description to the model, to the LLM, and it will create, again, let's say a tokenized list of sequences, and it will indicate which tokens are active for this description. Okay? So maybe just to write it, it's going to be data set. We are going to have tokenize, we are going to have tokens. So token and activation for that token which we denoted for Z. So let me see how to index this. We are going to have, this is again for the latent case, so we are zooming into or slicing each sparse feature vector by decade dimension. We are going to have, we're going to iterate over number of sequences, and this one is iterating over the number of tokens. So here again we can have J and I. Okay. And this LLM is also going to activate, give us a data set of neutral examples, meaning that here where some of these will be active, no zero, higher than zero, here they will not be. So these will be all 0 or less. Okay, and also in this methodology you don't need to request that, that this method actually gives you these activations. So it can just give you tokens, and some of these tokens are actually activating this description, and in the neutral data set, none of the tokens are activating the description. So giving this value, it's optional. So actually, let's think about the case where we don't have this method didn't give us the activation. It just gave us the tokens, where implicitly this LLM knows that some of these tokens will activate this feature, and in neutral examples, none of the tokens will activate the feature. Okay? Now, what can we do with this? What is kind of expectation that we can form from having a pair of data sets, one data set of tokenized sequences where some of these tokens activate the description, and where they are not activating the description. Any ideas? Yep.
We would expect that if you put those tokens through our sparse order that the vulnerability should be activated.
Okay, here it should be activated, and here it should, what should happen here with the neutral examples? It should not be activated. Or at least we want the activation in these tokens to be notably higher than activation in these tokens. And that's exactly what these set of authors are proposing. They say, well, let's take the activate examples, let's pass them through SAE, and let's measure the activation of the tokens that activate the description. So this is the average ZK for active tokens. And let's pass the other data set. And here we will have another average latent value. And we check whether the active one is higher than neutral. So in the paper, they are just checking whether it is higher, even and it's okay even if it's higher by some negligible amount. I think maybe one nice addition here would be to kind of enforce that it's statistically higher. For example, instead of averaging these Z values, you can form a distribution of activations in one data set another, and you can check whether these two distributions are statistically different, statistically far apart from each other. So for example, if there were two normal distributions, you would expect away from each other, which you can measure with t-test or something like that. But in their paper, they are just checking whether this activation average value in the active data set is higher than for the neutral data set. And of course, this again has a difficulty that you need to differentiate between this not happening and this LLM not being capable of producing examples like this. So you need to do additional analysis where you check that these examples are truly, like, you take a sample of at least a few dozen of them and you manually read them and you yourself think that, yes, this represents something that activates this feature. Otherwise, when you don't get this result, it can be not because the original description was bad, but because your LLM was not capable of producing these data sets. So you need to be a little bit careful when using this. Okay, questions?
So do we give any information about the SAE or whatever replacement model we have to that LLM? Because otherwise it just seems to, the task seems to be just find some examples that are within the topic of that description and some that are without.
Yeah.
So.
Yeah, I think that's sufficient, right? I don't think you need to, I'm curious why you think of the information about SAE.
I was thinking of, well, what if we just want to compare the descriptions that two different SAEs are giving me, which one is better?
Yeah.
So given that this LLM has no idea of these two, basically there is no distinction in terms of these two data sets that I
I
have.
think that's a feature, not the bug. I don't think you want your LLM that's judging the description in this procedure to have any information that would make it favor one or the other beyond the description it's receiving, right? So, first, here we have the description. It generates, the data, and in the end, it's just about confirming whether the activations are truly aligned with the data that is capturing the description, right? So I don't think you need to give any information to the SAE here. Yeah. Yeah. So. I'm trying to make an analogy with the other approach, but I don't know whether I'll be successful. But I will go over motivation of this one more time, which is if I had data which captures this feature, such as expressions of emotion, and I have data that doesn't capture that feature at all. Someone had constructed that data for me. In this case, an LLM, it would be even better if it's a person who is maybe more careful. But of course, then we have the limitation of scale. That's why we use LLM. So I have that data, and I want to confirm that the latent truly activates for that data if the description of when that latent activates is appropriate description for that latent. And if it is appropriate description, then this data that captures that description will be highly activated, whereas data that doesn't capture that description, that feature, will not be activated. So it's a sanity soundness check. And finally, the last approach that this paper presents is to also measure the effects on the output. So what they're going to do is they're going to increase the values, the activation of specific latent by increasing the let's say representation of let me start. I'm rambling. Let me start this over. So. Now we are going to move into into evaluation of this description by looking into effects of all of these on the next token prediction. So with next token prediction, we have some prefix, right? let's say this is our prefix, or context, or maybe prompt, whatever you want to do. And the model LLM that we are explaining, the original LLM for which we have actually built the SAE for, is designed to predict next token. So LLM gets this and then should predict the next token. So what these authors are also proposing is to try to, for here in the final representation of this last token in the preface, based on its representation is where the decision of what the next token is going to be, it happens at that position. So what if we take the latent of that token, so here 1, 3. So what if I take its latent, and what if I set it to some high value? So I activate it highly. Or I take some other latent, some random one, so some random value, and set it to a really high value. So I do this, and then I have tweaked the model in some way, and I let it to generate n tokens when random latent is highly active. So it generates D4, D5, D6, let's say, if my n equals 3. And I also generate here next tokens when I had set the actual latent to a high value. So I have these two sequences together with the prefix. One sequence is obtained when I had set the actual latent I'm zooming into to a high value. So basically I'm looking into, if I really put that latent to something really high, such as expressions of emotions, what you would expect here is that suddenly model is really widely wanting to predict things that are expressing emotions, right? So if I had made that single feature super important, way more important than anything else, then what I expect to see in these generating sequences that these sequences exhibit that pattern really, really, really highly, right? On the other hand, if I pick some other latent and I made that latent the most important latent, and assuming that latent is not emotions of expressions too, we don't have redundancy, here I should see sequences that exhibit some other pattern, right? So let's say if this was, related to scientific writing, suddenly I might see some terms that are commonly seen in scientific literature, right? So what I can do now is check whether when I have these two sequences, I can again ask an LLM which of these two sequences better fit my description of that latent, right? So I give the description to the LLM, I give it this sequence, and I give this sequence, and I ask which one is more aligned with this description. And if this latent is truly can be described with this feature, then what we would expect is that this one is selected here as the one which is more aligned with the feature, right? So here we get 1. If I will call this sequence K for latent K, and I will call this one sequence random. So I will collect 1 if sequence K is selected as more aligned with feature description. then you can average these over all the feature description to get one value for the entire SAE. Same here, right? So I get one if this happens, and then we can average these values over all of the features. Questions about either one of these? Is this clear? The method, how we do it? And the important difference is that here we're kind of working with input, right? We are trying to create this input data that exhibit the pattern, and we want the activations of that latent to be aligned with that. Here we are looking into how changing the latent to some high value will affect the output, the generation of next token prediction, and then we are checking whether description is aligned with that. Yes?
For method 3, couldn't the LLM make the token, then make the description K?
So second?
Yeah, for the description K, LLM makes the tokens, right?
Yes, so we have this description came from this LLM here, right? So that would be like, let's say Claude Opus 4.5. And then here we can use another LLM, completely different, like GPT 5.2. And this LLM will create the data, create the tokens.
It also can generate the token if already made the description, like the same token.
It can. So description here will be something, if you remember from Neuropedia last time, expressions of emotions. Here we are looking for data that has that pattern. So this data could look like, yay, today was an awesome day, right? So it's going to be a sentence that has that pattern. So it's a slightly different text, right?
Okay.
I don't expect here you will, LLM that's capable of following instruction will just repeat the description of the feature. It will generate data that has that description. Yeah.
Okay.
John, sorry, what's your name?
I'm Jay.
Jay. Okay, Jay and then John.
So there's no guarantee that option 4 will work, right? Because there's no guarantee that token 4, 5, 6 will have a high attention to token 3. It could just, even though token 3 has high activation in feature K, if token 4, 5, 6 don't have attention to that, then...
Okay, let me go over a few details and then let me see whether that answers here. So here I'm zooming into this last token, just because in general when we do next token prediction with decoder-only transformers, we take the last token's final representation to make the next token prediction, right? So this is why I selected this one in particular, and this activation here can be small or high already. It doesn't really matter. I'm going to artificially tweak it to be really high, right? So, so what the actual activation here is, it doesn't really matter. I'm just forcing it to be really high such that the next token prediction is encouraged to focus, the probability mass of where the vocabulary to be aligned with that feature. Okay, now all that said, can you repeat your question just to be sure that we're on the same page?
So yeah, my question's about like the attention it gives to token 3, like the likelihood of what token 4 is. It could be more weighted towards token 1 and 2 instead.
Okay, so you are saying, well, if this token is kind of ignored by the next token prediction mechanism, this won't work.
Yeah.
And you are right, but that won't really happen. What is this token's representation? It captures, first of all, everything that had preceded, right? And it is the representation you will use to make the next token prediction. So whatever are the latents here is relevant for the next token prediction. I think that situation, although everything is possible in our world, I think it's not a serious concern. Yeah. Jonathan, did you have a question? Got it.
I kind of just thought about this now, but why in the 2 do you do the sum of all the token sequence to get the accuracy instead of just using the last one?
So here, okay, I think this next token business is gonna confuse you a lot. So in the previous methods, we needed we didn't need next token prediction. We needed data, and we needed to check whether what we expect to happen with that data will happen, right? So our data here are, for every token we have a sparse feature vector, right? So that's our data, right? And we don't need to zoom into last token in the prefix because we're not looking at this evaluation metric from the point of view of next token predictions, right? We are just looking when I represent tokens and when those representations are reconstructed with sparse feature vectors, whether what is actually observed matches with what we can simulate based on the description alone, right? So this is a long answer. Short answer is we haven't formed this evaluation from the standpoint of next token prediction, so we didn't need to zoom into the last step. Right? So here we are framing our evaluation from the point of the next token prediction, and so therefore we have zoomed the last one.
Okay, that makes sense.
Yeah.
What are we gaining by doing this next token prediction method as opposed to the other methods which are just relying on the data that we already have?
The motivation here is that all of these other data evaluations are specific only to the input, but when we produce representations, dense and then sparse reconstructions, all of that serves to actually do the next token prediction, right? These representations, all the other evaluations are looking at the, are completely ignoring why are we producing these representations. We are just embracing, we produce these representations and let's check whether it makes sense. Only here we are embracing the fact that these representations are produced such that we will eventually do next token prediction. And it's the first so-called output-centered evaluation of feature description, a major contribution of this paper. So here they're looking into okay, we have these features and they are all serving to make next tokens. So let's frame our evaluation of this feature description in the output-centered way as well. Everything else was input specific.
Okay.
Yeah. And to also be clear, today you will want to report not just one of these metrics. Maybe you don't need to report simulation-based and binary accuracy-based. You can pick, let's say, just binary accuracy. But these additional one would complement this second one. So you would report both the second, third, and fourth evaluation, and potentially many more as they are emerging. Because all of them have maybe a slight confounder, such as here the capability to produce this data, the capability to predict whether this is active or not active, right? So you have a lot of moving pieces here, and having various metrics that do things slightly differently will just give you a more robust evaluation. Okay, let's stop here, take a 5-minute break, since this was a lot, and then we will recall. So let's continue, guys. If you can take a seat, please. All right, let's continue. So now we have covered our basic SAE setup fully. We had, just to repeat, for a given input, we produce a representation, let's say output of MLP at a given token, and then we reconstruct this token using a sparse feature vector together with feature directions that are stored as columns in the decoder weight matrix, right? And we said, okay, we need to give some meaning to each one of these latents, meaning dimensions of the sparse feature vectors. So later when we say if we choose only 3 top activating features, we can say, well, in this representation, at this token, the 3 features that are really active are this and this and this, and that will kind of inform us about some behavior of the model that we are examining, such as next token prediction. And remember, you can, last time we used Neuropedia to write some prompt, and then we could zoom into one of the tokens, let's say last token, and we could see these top features and kind of think about why those features are activated and how this can influence the next token prediction. Now, we didn't talk about how do we actually evaluate the SAEs themselves. We talked about how do we evaluate whether the descriptions are good. So we didn't talk about SAE evaluation fully. That's one thing that we have skipped. And I mentioned that SAE will have, due to the way they are trained to, they are optimized for reconstruction and sparsity. This will introduce some problematic behaviors and or problematic phenomena, let's say. And we will want to avoid that problematic phenomena. So we are going to then talk about how to improve SAE 3. So we are going to see some SAE variants. So this is next on our agenda. Obviously, not everything will be done in the following 15 minutes. So let's talk about SAE evaluation. Let's say I'm training an SAE. I trained it. I haven't produced any descriptions yet. What makes sense to check to see whether my training run was done successfully, or at least it didn't fail? What kind of metrics make sense to check? The way you can think about this is, what are we training an SAE to do? What is the training objective? So if the training run failed, that objective failed. So
If I can measure the error before and after passing it through.
okay, and can you be a bit more specific? What is an error here?
Like the residual difference between the input vector and the output vector.
Yeah, so first, let's call this core metrics, right? The first thing that makes sense to check is whether we are reconstructing test data, right? So reconstruction on the test data, which would be the MSC loss, which is the difference between the original activation and the norm, L2 norm of the difference between the original and reconstructed activation squared. So original, reconstructed. And what is better, lower or higher? Lower, right? So lower is better. What else? Sparsity, right? And remember, I think you made a mistake a few times already, saying that this reconstruction should be sparse. It's not the reconstruction, but rather the sparse feature vector that we are going to use. So we can use L0 norm of the sparse feature vector, which is just the number of values you see that are non-zero. I didn't mean to call anyone out, just to be clear. We all make this mistake. Okay, so these are two common metrics you're going to see, but the issue with these metrics is that, and let me emphasize this, that we are evaluating this on the test set. So SAE test set. The issue with these two metrics is that yes, we use these objectives to train our SAEs, but what we care about is not these, I mean, in some sense we do care about this reconstruction and sparsity loss, but what we really care about is that we get features that are useful for downstream cases, right? So these, you will see things such as, oh, we can use this SAE feature for safety reasons, like I can, if there is some kind of hidden objective induced into an LLM, I can use this SAE to reveal this hidden objective. Or maybe from a more human-centered or human interaction point of view, you want your person, let's say a clinician, to collaborate with an AI model that is maybe assisting with differential diagnosis, and you want these SAE features to help them in some way, maybe to recognize something about the problem, a situation of someone's condition that they missed, or maybe to kind of gain trust into this assister in their clinical decision making. So we have these really ambitious, goals, which are definitely not captured by how much we reconstruct and how many features, right? So these are just core metrics. I would like you to think about this as your soundness checks for your training runs. You will see some kind of attempts to move from these core metrics to utility by checking how much, if we use SAE, how much our language modeling loss is changing, right? And just by replacing original representation with the activation, original representation with the reconstruction, you shouldn't lose the capability to do language modeling, which is the core behavior of LLMs. Again, next token prediction and language modeling is correlated with all of these good, useful tasks we like, but the loss itself also doesn't quite capture the downstream utilities. So for example, even before interpretability and everything, you could measure language modeling loss or perplexity, but that measure wouldn't correlate with accuracy on downstream tasks. So again, what I'm going to say is kind of an attempt to move away just from the core metrics into something which is more associated with utility, but it's also very rudimentary. So utility here, one thing you're going to see is the cross entropy, or if you have taken my classes before, I like to use a negative log likelihood term. So these are the same when we use neural networks with softmax. So cross entropy or negative log likelihood loss for language modeling. And just because not everyone had taken an LLM course to repeat, we have, again, when we do language modeling or next token prediction, we have some prefix. So these are going to be tokens 1, tokens 2. Let's say we have 4 tokens, and now we are trying to predict the 5th one. And to calculate loss, we actually have information about what is the next token, because we scraped some data, right? We took some paragraph, let's say from Wikipedia, and we know what actually appears as the next token. So our loss becomes the negative log likelihood of seeing D5, which is the next token that actually appears in the data. So token that's next in the data. Given this prefix. Question for folks who didn't take my NLP course, how do I get this probability? There was some okay, yes. Softmax. So yes, the probability of D5 given a prefix is softmax, and softmax So we take some output matrix and we multiply it with the final representation of T4. I will just use a vector of T4 to denote that. And then this will give me a vector of the size of the vocab. What I need to do to get this probability? You can take it.
T5.
Yeah. So we need to index it that I started here with 1, so not 0, so we are going to take 5. If I had started with 0, we would have taken 4. So this is the softmax of a vector. This gives me a vector of logits of the size of the vocab. When I give a vector to a softmax, I'm going to get the same size vector, but now the values are split between 0 and 1, and they sum to 1. And if I want the probability of this token, I actually have made a mistake. It's not 5, because this appears at the position 5. It's rather the vocabulary index of token 5. So let's say next token is token cat. Cat will have certain vocabulary index, and it might be, I don't know, 3,000, right? It can be completely different from the position here, which is 5th position. So I'm going to slice my softmax vector by the vocabulary index of that particular token. Okay, so that's the language modeling loss. Going back to what we are doing here, we are going to measure the change in model performance when replacing activations with the corresponding SAE reconstructions during the forward pass. So we are going to measure how much the negative log likelihood changes when, instead of using the original representation X here, for this token, I use my reconstruction. What is the idea here? Should this loss change a lot or little?
Change a little?
Yeah, right. So if my reconstruction is a good reconstruction and the behavior of the model won't change, meaning the next token would be predicted exactly as it would without, interpretability layer, then this should change a little. However, we are going to complicate this, so what people are actually measuring is the following thing. So here we have H original is the loss, the original loss. So the loss we get for the next token, the negative log likelihood loss, for the next token when we didn't do anything to the model. It's just the original model's loss. Then we're going to have H0 is going to be the loss when the original representation is replaced by a 0 vector. So it's ablated. The loss when X is ablated. And that's going to be our denominator. So okay, so here we have H star, and again we are checking the difference. So we are basically saying we are having this kind of control to tell us, okay, if I had completely removed this original representation from the model, how much should the loss change? And here I'm checking, well, if I had, instead of the original representation, my reconstructed representation, how much the loss would change with respect to ablating the representation. And what we want to have here is that this difference is kind of the same whether we use the original or the reconstructed loss. So this will go from 0 to 1, but here higher is going to be better, right? This is desired. And we want to have the similar change using H star or H original. Okay, so You can also, I'll finish with this. This is one way to see how using these reconstructions can influence the next token prediction. Other way is to use the KL divergence between two, of course, distributions. But distributions we are going to use are these softmax vectors from the original vector, and when we use the reconstructed vector. So general equation for KL divergence between two distribution Q and P is the sum over x, qx log of qx over px. And here we are going to have Q is going to be Q can be distribution you get original softmax, let's call it like that, and P can be softmax we get when we use x instead of x hat, which is the reconstruction instead of x. And again, we want this divergence to be as small as possible, so lower is better. Okay, so let's stop here. Next time we are going to talk about problematic phenomena and various things we can do to change in SAE training to overcome these problematic phenomena, and then